Right, so we're moving on to equilibrium rate now. So give me the Haber process, which we all know and love. We've done it umpteen times before. Describe and explain the effect of increasing pressure on the rate of reaction. So you don't need to talk about equilibrium, just on the rate of reaction. Well, what is the effect on the rate of reaction? If I increase the pressure, the rate of reaction will increase because my molecules are closer together and therefore there are more collisions per second. It then gives me some concentrations and it wants me to calculate Kc. So remember, Kc for this reaction is going to be the concentration of your products divided by the concentration of your reactants. Remembering that because you've got 2 ammonias, you square it, because you've got 3 hydrogens, you cube it. You put those numbers into this, and again, I would recommend that you work out each of these numbers first. So don't try and do everything at once. H2 is going to be 2. Times 2 cubed. So work out 0.877 squared and then 1.2 times 2 cubed. And then work out what you should get, which is 0.0801 for that. Right, it then wants me to explain how the following changes would affect the amount of ammonia present in the equilibrium. So how would a catalyst affect it? Well, there'd be no effect, and the reason why is because you add a catalyst, it speeds up the rate of the forward reaction and the backward reaction by the same amount, so there's no change in concentration at all. A higher temperature, well, remember this is an exothermic reaction, so if I increase the temperature, it will move in the endothermic direction to try and reduce the temperature, which is to the reactants. So the concentration of ammonia will decrease because the reaction is pushed in the endothermic direction towards the reactants. Right, it's quite a nice yield question now. So 1 ton of ammonia from the high process is reacted with carbon dioxide to prepare urea. And I make 1.35 tons of urea. Calculate percentage yield. So first of all, you work out your moles of ammonia, which is your mass. Remember to convert from tons to grams, divided by the molar mass of ammonia, which is 17, to give you 58824. Notice that for every 2 ammonias, you only get 1 urea, so you need to divide that by 2 to get the number of moles of that, and then times by the molar mass of urea, which is 60, to get my theoretical yield of 1764720. So my percentage yield is what I got, 1.35 times 10 to the 6, divided by what I hope to get, 1764720, times by 100, and that gives you, let's have a look, 1.35 10 to the 6, divided by 1764720, that gives you, times 100, 76.5%. Right, so question 4, a lot of information to get through here, but just breathe and go through it. So here we go. We've got to identify 4 different solutions: ammonium sulfate, sodium chloride and potassium bromide. They've given me universal indicator and the following reagents. Someone in your group says, well, let's add 1 centimetre depth of each solution to separate test tubes, add some barium chloride, and we'll see a white precipitate for the sulfate ions. So 2 of them will form a white precipitate. Okay, great. how can we expand this plan so that we can identify all 4 solutions, including observations and conclusions? So what they've said is this beginning of the method has allowed us to identify which 2 are sulfates. So we've worked out which 2 of these, so I know that I've got my 2 sulfates. I need to now tell these apart. How do I tell these apart? Well, if I add to both of them sodium hydroxide solution and warm it up, and I test the gas produced with some universal indicator paper, which I believe I've been given. Yeah, I will note an alkaline gas being given off, which is ammonia, and therefore I'd be able to identify the alkaline gas, the test tube which gives the alkaline gas off of ammonia is ammonium sulfate. The one that doesn't produce a gas is therefore sodium sulfate. So I've worked out those 2. I now need to turn my attention to the other 2, sodium chloride and potassium bromide. How do I tell those 2 apart? Well, remember, I can use silver nitrate to tell those 2 apart. So to each of these solutions, I would add silver nitrate solution, and I will see for the chloride a white precipitate and for the bromide a cream precipitate. But it's very difficult to tell them apart. So what do we add? We then add dilute ammonia, and silver chloride, which is produced when I add silver nitrate to sodium chloride, will dissolve in dilute ammonia, whereas silver bromide will not dissolve in dilute ammonia. So that would tell those 2 apart. So I'd be able to tell all 4 solutions apart. Right, okay, so barium chloride now has a high melting point, dissolves in water that can be used to test for sulfate ions. Okay, yeah, we kind of established that. Draw a dot and cross diagram to show the bonding in barium chloride, showing outer electrons. So it's going to be ionic because it's a metal bonded to a non-metal. Barium, of course, is in group 2, so it's going to form a 2+ ion. Each chlorine atom will gain 1 electron from the barium. So I will end up with 2 chloride ions like so. I'm sure your circles will be much better than mine. A solution of barium chloride can be made in a lab using HCl. Suggest a compound that reacts with HCl to make barium chloride. Well, barium chloride is of course a salt. So what do I need to react with hydrochloric acid to produce barium chloride? I could pick barium oxide, which is going to be a nice base. I could have barium carbonate, barium hydroxide, anything that's going to react with an acid to produce a salt. Note, it's got to be a compound that reacted, so don't put barium, although barium would react with hydrochloric acid quite violently to produce barium chloride, it wants a compound, so don't put barium. Okay, so describe the mechanism for the alkaline hydrolysis of 2-iodopropane, name them curly arrows, etc. So the name is nucleophilic substitution. My nucleophile is going to be OH minus. Don't forget your lone pair on the oxygen. Your dipole, that carbon is going to be delta plus and the iodine delta minus. It attacks there. That bond breaks to go to the iodine to give you your product CH3, COH, H, and then coming off here is going to be C3H, 7, like so, plus I minus. And it's a good idea to just put the lone pair on the I minus as well. Okay, so it now wants me to plan an experiment to prepare 0.1 mole of 2-bromopentane from pentanetol. So how much pentanetol do I need? Well, I need 0.1 mole of it. The molar mass of pentanetol is 88, which means I need 8.8 grams of it. And then how do you do it? Well, you would warm it with sodium bromide and sulfuric acid. Right, so nice, this should be quite straightforward. About isomers really. So I've got to eliminate water from pentan-2-ol, which I've drawn up there, to produce a mixture of organic products. Give the names and structures of all the organic products in the mixture and explain how it leads to different isomers. Well, effectively it's because this group has got to be eliminated, but the hydrogen could be eliminated from the first carbon. If that gets eliminated, I would make CH2, CH, CH2, CH2, CH3, which is of course pent-1-ene. However, if I eliminate those two neighbours, I'm going to make pent-2-ene. So I would make CH3, CH double bond, CH, CH2, CH3. So pent-2-ene. But for pent-2-ene, I can make both the E and the Z isomer. So I could make both this isomer, or I could make that isomer there, where of course this is the E isomer and that is the Z isomer there. Or alternatively, this is the cis and that is the trans isomer. So I can make E-but-2-ene, sorry, E-pent-2-ene or Z-pent-2-ene as well. And then why do I get these two isomers? It's because you cannot have rotation around the carbon-carbon double bond, and for these two isomers I have different groups attached to each carbon in the carbon-carbon